Welcome to Logger Lectures Online, part of our series of digital lectures presented by the McMaster Alumni Association. These in-person and online lectures are named after McMaster graduate Albert Abram Logger, a great believer in the value of lifelong education. He created the Albert Abram Logger Foundation, which supports several organizations in their efforts, including the McMaster Alumni Association.
Unstructured search, and these algorithms were designed Good evening. My name is Chris Gajansky, and I work on the alumni team here at MAC, arranging events that showcase our exceptional faculty and alumni. We're always working to keep alumni and friends connected to and proud of McMaster. And tonight we have a speaker that is both an alumnus and a faculty member. So you are in for a double treat. Although we cannot organize events that bring people together in person, we do love that our alumni and friends can participate no matter where they are. And even if you're not here with us during the live event, you're able to watch it later on your own time. Tonight, I'm so very pleased to introduce you to Dr. Janok Bhattacharya. As I said, he's both an alumnus and a faculty member. After graduating from Memorial University in Newfoundland, he embarked on a career in Alberta in the resource industry. He noted many of the most exceptional geologists were McMaster graduates and ended up doing his PhD at MAC with Roger Walker, one of MAC's leading geologists, as his supervisor. He went on to roles in the private sector, but returned to academia. And it was when Janok was a faculty member and chairholder at the University of Houston that he began a conversation with Susan Cunningham, who's also a MAC grad, and she's also a supporter. The conversation led to his return to MAC as the inaugural Susan Cunningham Research Chair in Geology in 2013 in the School of Earth, Environment, and Society. We asked Janok to speak to our alumni tonight because our McMaster Virtual Book Club is currently reading the book called The Sixth Extinction, An Unnatural History by writer Elizabeth Kolberg. In searching for a faculty member who might be able to speak to this topic, we discovered that Janok is writing a textbook on geological and biological history, which will include chapters on climate change, mass extinction, and the sixth extinction. Lucky us and lucky you. Before I introduce you to Janok, a bit of housekeeping. You will be able to ask questions during the event using the Q&A bottom at the bottom of your screen. We received so many questions though before, so all I could say is we're going to do our very best to get to all of the questions. But I do encourage you to add your questions sooner rather than later to make things a little bit more manageable at our end when we get to the Q&A. Thanks so much and welcome, Janok.
Thank you, everybody. Hopefully you can all hear me well. It's certainly my delight to be talking to you today. As Chris told you, I'm the Susan Cunningham Research Chair in Geology here at McMaster, and I'm both a proud alum, an employee, and also a donor myself. The focus of the talk today is on this issue of extinctions. And when Chris contacted me, she advised me that a group of alumni are reading a book by Elizabeth Kolberg called The Sixth Extinction, a book that I happen to have read. And of course, I'm writing a book on the history of Earth and life. And so I thought maybe I could tell you a little about my knowledge of major catastrophic events in Earth history and the implications for the ongoing changes that many of us are concerned about. So the title of my talk is Mass Extinctions, Supervolcanoes, and Asteroids. So I'm going to start with a little, just a little, not a quiz. Professors like to have quizzes. So I have a series of statements in here. Anthropogenic warming will likely destroy a planet, make Earth uninhabitable for all life, cause a mass extinction, cause some extinctions, cause significant stress on many populations or on local populations, or have no long-term effect for life on Earth. And throughout the talk, I think we've set it up that you can sort of vote on which of these you're most concerned about, or which of these statements you think best represents something that might be accurate. And we'll return to that question at the end of the talk and see if you're still thinking the same thing. Now, we do have a course at McMaster called Natural Disasters, and it's sometimes worthwhile thinking about the disasters that we may or may not be familiar with. So here's just a list of disasters, and the next question is, have a look at this list. Which of these disasters is the deadliest? And this slide has actually changed since I first put it together a few years ago. Is it the current COVID pandemic? I lived in the States during 9/11, and that was certainly a very dark day, but how many people actually died from that? That, of course, was a man-made disaster. Some of you may remember the 2004 Boxing Day earthquake in Southeast Asia. And exactly a year before that earthquake, I was on vacation in Thailand. And I remember I was in a gym on Boxing Day in 2004, and I saw the hotel that I'd stayed in a year before being destroyed by the tsunami. Many of you probably didn't even know there was a big earthquake in 2003 in Bam, or the Tangshan earthquake in China in 1976. If you've read Simon Winchester's book on Krakatoa, one of the largest volcanic eruptions in 1883, and about a year ago, or last September, I was in Italy and visited Pompeii and Herculaneum and witnessed the destruction of Mount Vesuvius that destroyed those Roman communities in '89. So here's the list of deaths. The COVID by far is much higher than any of them. 1.3 million globally so far, and we're not even a year into it. The 1976 Tangshan earthquake in China killed almost 250,000, as did the Boxing earthquake and tsunami. And the other disasters are much lower. And of course, the 9/11 attacks, as dreadful as they were, the numbers were relatively trivial compared to some of these much more deadly natural disasters, such as pandemics and earthquakes and volcanoes, which is, of course, the focus of this talk. But of course, the reality is none of these events compare even vaguely the kind of catastrophic mass extinctions that have occurred throughout the history of life on Earth. Jack Sepkoski was a paleontologist at the University of Chicago, and by the time the 80s rolled around, there was enough data collected on fossils and collections throughout the world that he began compiling statistical assemblages of lists of fossils and groups and families to look at how those had either diversified, such as during the Cambrian explosion or the Great Ordovician and Biological Diversity event, versus these catastrophic die-offs where we see these abrupt vertical cliffs that represent massive loss of diversity, and these document the major extinctions. Sepkoski coined the idea that there was a distinct Cambrian fauna that witnessed explosion with sort of a long trailing die-off punctuated by a few events. That was replaced by the so-called Paleozoic or old life fauna that lasted for almost 500 million years. And they eventually were replaced by the so-called modern fauna, which dominate the oceans today. So these are the great 5 extinctions that Sepkoski recognized, one at the end of the Ordovician period, one at the end of the Devonian period, the greatest extinction of all time at the end of the Paleozoic or the Permian period. We're going to talk about that one in more detail. Another one in the early Mesozoic, at the time of the dinosaurs in the Triassic. And of course, the extinction that probably everyone's heard about, which ended the Mesozoic period and ended the reign of the dinosaurs and ushered in the sort of the world that we are more familiar with. So here's an example of, so we have percentages of genera. So life is organized into domains, kingdom, orders, families, genus, and species. And so this is showing the genera through time. And what this shows is the extinction rate for the last sort of 550 million years of Earth history. And you can see that there's some major spikes here with on the scale of 50% of all genera going extinct. These are the 5 big ones. There are some pretty major extinction events in the Cambrian, but the fossil record is poor during those times. So we're not sure if that truly represents the full diversity of life on Earth at that time. And the end Permian, which we're going to talk about, was preceded by this Capetanian extinction. And then the Cretaceous Paleogene extinction used to be called the KT, which stands for Cretaceous Tertiary. The word tertiary is not used anymore. Now we say Cenozoic. And the first period of the Cenozoic is the Paleogene. So it's just looking at the slide, there's a few things to note. There's obviously this kind of a background rate of extinction. Looks like that may have decreased through time, but of course we have more knowledge of what's going on in the world today. The further back in time, the more sparse the record of life on Earth gets. Mass extinctions seem to occur when the rate gets above about 20%. And you could argue maybe above 10%, it starts to look more spiky. So of course, one of the big questions that we need to think about in order of understanding a chart like this and its application today, is what is the rate of extinction versus speciation? At any given time, new species are appearing and other species are being replaced or going extinct. A mass extinction occurs when the rate of speciation is unable to keep up with the rate of extinctions. Okay, there are many more than 5 extinction events, and there's always extinction going on. There's always a background rate of extinction. Again, something on the scale of a few percent. The question today is what triggers these mass extinctions when life is no longer able to keep up. So let's just look at one of my favorite group, the Dinosaurian clade. And the dinosaurs are a pretty good example of what we call relatively gradual extinction. If we look at the gigantic sauropods, the earliest Triassic protosauropods had an upright gait and were quadrupedal some of the time. They evolved into the gigantic sauropods, and the sauropods persisted right up until the last day of the Mesozoic. I was involved in the collection of this guy here, who is now at the Houston Museum of Natural History. That's the Alamosaurus, and I worked on the site where they discovered that fossil neck. The actual neck is actually next to the dinosaur, and this is a cast of the animal, and it was one of the biggest sauropods that ever lived on planet Earth, and it was alive and well right up until the end of the Cretaceous period. And so in this case, we see a gradual replacement of one sauropod by another, so I would call that a within group or within clade speciation. As opposed to complete replacement by a different sort of group of organisms altogether. And we see a similar transition, the evolution of the pteropods, sort of the earliest pteropod or carnivorous dinosaur, the Herrerasaurus found in Argentina, a Triassic predator, totally bipedal, that morphed into the rather larger Allosaurus that was common in the Jurassic period. And of course, culminated in one of the largest pteropods, T-Rex, which everyone, of course, has probably seen in movies or museums. And T-Rex and Alamosaurus went extinct on the same day in the Cretaceous 66 million years ago. And we're going to talk about why that happened. Okay, so for those of you who aren't geologists, it's really critical to understand that our planet changes profoundly. So here's an example of paleogeographic reconstructions of what the Earth looked like in deep time. In the Paleozoic, many of the continents were stuck together in this landmass called Pangaea. A lot of Pangaea was stuck down in the southern hemisphere on the South Pole. Antarctica is still there today, and it's been down there for an awfully long period of time. But back in the Paleozoic, Saudi Arabia was down there, Australia was down there, South America was down there, and all of those continents experienced massive glaciations. Interestingly, that massive glaciation was a result of the evolution of land plants. The land plants in the Devonian and the Carboniferous stored carbon, emitted oxygen, and ultimately pushed the world into what we call an ice house because they were removing carbon dioxide, which is a greenhouse gas. What's interesting is at the end of the Permian, there was a massive change, the end of that glaciation, and the Earth was driven into a greenhouse, and 90% of everything went dead. What caused that greenhouse? And we'll talk about that. As we go into the Mesozoic, we see that Pangaea breaks up, and we go into a warm, humid water world, which dominates the Cretaceous. And the Cretaceous was a warm, humid water world, a greenhouse time, right up until 66 million years ago, when something really horrible happened that ended the Mesozoic era. It was another probably 50 million years before the Earth was driven back into an ice house period, which we're experiencing today. So one of the points is that these tectonic plates cause the continents to shift around. Oceans open, ocean close. Continents can go from a tropical to an equatorial to a polar position and back again. And of course, all of those changes are things that life has to adapt to. These climate and tectonic changes, for the most part, occur pretty slowly, and so life changes, but it's able to more or less adapt. Okay, and continents change position because of plate tectonics, and those processes occur at the scale of millions to hundreds of millions of years. Climate change is a result of the orbit of the Earth around the sun, which changes it enough to change the overall temperature of the Earth. And that's a much faster process that occurs with incredible regularity at 10,000 to 100,000 year cycles. And right now we're in the middle of we're in between glacial periods. And if there were no humans, we probably should be going back into a glacial period. And of course, sea levels also change as a result of short-term climate as well as long-term tectonics. Of course, the planet's atmosphere has changed profoundly. Before there was life on Earth and before there was cyanobacteria, Earth's atmosphere was carbon dioxide, methane, and nasty stuff that we can't breathe. Once photosynthesis developed and began creating oxygen, they fundamentally changed the geochemistry of our planet during the great oxygenation event about 2 billion years ago. During the Carboniferous, as a result of all that storing of CO2 and all of that release in oxygen, the Earth got extremely oxygenated, and the next thing you know, you had gigantic insects. And of course, life on Earth has to adapt to all of that change. Sometimes life is not successful, especially when the change is really fast. So let's look at a couple of these extinction events, okay? So we'll start with the Cretaceous Tertiary extinction because that's the most recent of the great extinctions. I'll just point out that India at that time is in the southern hemisphere. Australia is still attached to Antarctica, but a lot of the continents are more or less in their modern positions. However, North America is largely flooded, and South America and North America are not connected. Okay. So the KPG extinction caused about 75% of the species on Earth to extinct. All of the non-avian dinosaurs went extinct. The birds, which are considered avian dinosaurs, survived. Mammals survived, all the flying reptiles, the pterosaurs, the great swimming beasts, mosasaurs and plesiosaurs, the squids in the shell or the ammonites, and a lot of organisms that you may or may not have heard of went extinct. Plants, fish, birds, most of the cold-blooded reptiles and mammals somehow made it through. Of course, one of the questions is why? Why do some survive when 75% of everything else goes extinct? There's been lots of hypotheses for the end of the dinosaurs. I'm not going to go through them all. The two main ones focus on a volcanic supereruption producing a large igneous province and a major extraterrestrial impact. So the large igneous province in question is referred to as the Deccan Traps in India. The word traps comes from the staircase morphology of the exposed basaltic flow layers. The traps cover an area of thousands of square kilometers, and they're thousands of meters thick. Okay, what was happening is India was moving north as the Indian plate moved north, and there was a hotspot located around here. So and that hotspot's maybe shifted around a bit, but that hotspot was stuck right on India and spewed out this massive volume of volcanics right at the end of the Cretaceous period. And right now, that hotspot is located at Reunion Island, and it's still hot today. Okay. So what causes these hotspots? The hotspots are driven by these mantle plumes. So the Earth consists of a series of layers, and the sort of outer part of the Earth consists of thousands of kilometer thick unit of rock that moves extremely slowly, centimeters per year. It drives the movements of the plates that cause earthquakes and volcanoes, and at areas where the mantle upwells, it can sometimes upwell in a distinct sort of plume, and we call it a mantle plume. And those plumes can flare up and they can cool down, sometimes with catastrophic effects. They are very slow, and they sort of cycle at time scales of 50 to about 250,000 years. So tens to hundreds of millions of years. So they don't just pop over overnight and go down again, okay? It's not like the weather. You may all be familiar with Hawaii. So there's a hotspot that's located right here. Originally, the Pacific plate moved north, producing the Emperor Seamounts, and then it shifted northwest, making the Hawaiian Islands. And of course, the island of Hawaii sits right on top of Mauna Loa, which is the active volcano. In the questions, somebody asked about Yellowstone, and indeed, North America is moving to the north, to essentially west, over a hotspot. So 15, 20 million years ago, that hotspot was right underneath Washington and produced the Columbia River basalts. There's a photograph of those layers of basaltic lavas and the columnar jointing that characterizes that. And of course, right now, that hotspot is on the Yellowstone and feeds the geysers, such as Old Faithful. And of course, there is some massive calderas and fairly recent volcanics that have tracked the trail of that hotspot, and future flare-ups are indeed expected. We know they're going to happen. The big question, of course, is when. Now, what do volcanoes do? Well, volcanoes spew ash into the air, and that can cause global cooling. Krakatoa blew up in 1883, and a year later, there was increased acid rain from the sulfate, and there was about almost a half a degree drop in temperature. Now, those aerosols and ash don't last very long, and they fall back out, but they are able to cool the Earth down for a period of months to years. Okay, volcanoes can spew toxic metals, halogens such as chlorine can interfere with the ozone layer, and the sulfur dioxide that's released can produce acid rain. If there's carbon dioxide released, a lot of that gets absorbed by the oceans, and that can cause a change in the pH, producing ocean acidification. It is important to remember that the residence time for these materials spewed by volcanoes is variable. CO2 can take hundreds of years to dissipate. Sulfate aerosols can dissipate in a few months or a year or so. And of course, small volcanoes like Krakatoa don't cause mass extinctions. Large igneous provinces do. But what else happened at the Cretaceous-Paleogene boundary? So it's also thought that a huge 10-kilometer extraterrestrial object, and it may have been an asteroid, it may have been a comet, doesn't really matter much which it was, because it was the effect of the impact that pulverized a massive amount of seawater and rock that it hit that caused the damage, as opposed to the pulverization of the actual bolide itself. And the evidence includes enrichment of iridium, which is an element that's rich in meteorites and asteroids, but not very common on planet Earth today. In addition, the impact shocked the mineral quartz, which has no natural cleavage in it, but when you shock it with an impact, it can actually create dislocation planes in the crystals that can only be produced by massive shocks. Tektites represent material that's blown up into the air and fall back down again. And of course, anytime you have a massive bolide hit the ocean, that's going to create one heck of a tidal wave or tsunami. Eventually, they actually discovered the buried crater on the Yucatan Peninsula in Mexico. So the discovery took some years. Lewis and Walter Alvarez was interested in looking at the sediments across the Cretaceous-Paleogene boundary. And he said, look, iridium falls as solar dust on the Earth at a very constant rate. And if you have more iridium in a sedimentary layer, it means it's deposited slowly. If there's less iridium, it means it was deposited fast. And his dad had the lab that could measure these microscopic parts per billion of iridium. What was interesting is when they sampled the boundary clay layer, there was way too much iridium there. Way too much iridium that could be accounted for by the slow fallout from solar dust. And Lewis said, well, that might represent some sort of an impact. And that developed the hypothesis that maybe something really large hit the Earth right at the Cretaceous-Paleogene boundary. Here's the data that they showed. You can see sort of the background iridium layer, and then it shoots off to scale. You notice there's a little change in the scale there, and you've got 3 parts per billion in the clay layer at the boundary, as opposed to tenths of a parts per billion is the normal background. Similar iridium anomalies were found in Alberta at the Cretaceous-Paleogene boundary there. And iridium was found at all KPG boundary sites worldwide. And it's looked like they kind of look like perhaps they centered on the sort of the circum-Atlantic and maybe the Caribbean, the iridium. There's the Deccan Traps in India, and that's the site we'll talk about next, which is where they actually discovered the crater. So the other thing that the impact does is obviously you can get layers of ejecta, so material shot up into the air and then falls back down again. It has a very distinctive appearance, and it's graded because the big grains fall first and the smaller grains fall later. The liquefied rock shoots up into the air and crystallizes as glass beads, and they fall back down to the earth. And here's an example of quartz that's natural quartz. You see it has no striations in it, but when you shock it with an impact, it produces these very distinctive crystal locations that can only be produced by an extremely aggressive short impact. Eventually, they found a circular feature using geophysical methods and discovered the crater. And the crater is big. It's 300 kilometers diameter. It's buried under 20 kilometers of overlying material. And of course, because the rock melted, we're able to date the actual time of melting. And the impact happened 65.91 million years ago, plus or minus about 100,000 years. And that's a pretty precise date for a rock that's that old. Drilling, of course, actually sampled the impact breccia that was produced by the impact. So the force was incredible. Meteors moved about 72,000 kilometers per hour, and the energy of the deceleration of that when it hit the impact produced more energy than 10 billion times the energy of one of the atomic bombs used in World War II by comparison. There's an example of the breccia that they found. The impact pulverized hundreds of thousands of cubic kilometers of rock and seawater, and all of that ash, dust, carbon dioxide, sulfur dioxide was spewed up into the atmosphere. And obviously that had an enormous impact. So what are the kind of impacts? Obviously there were immediate effects, such as the wildfires that would have been produced by these red hot glass beads falling back to Earth. Anything in the path of the immediate destruction would have been wiped out immediately. The generation of carbon dioxide, because of the pulverization and vaporization of the limestone, would have been absorbed by the oceans and caused ocean acidification. And it's probable that there was so much ash, soot, and aerosols that it shut down photosynthesis for months and possibly as long as years. And the ocean acidification may have lasted longer, decades to centuries. So here's an example of a map of the world with the impact site, and the tsunami deposits have been found all around the Caribbean area. And the tsunami would have been a tidal wave about 100 meters high. A recent discovery way up in Montana found evidence of a river deposit in which there was evidence that the tsunami pushed the water all the way up into that river, such that the water flowed in the opposite direction. What's really interesting is you can see the actual little impact structures from the glass beads. There's a thin section that shows the glass beads. And here are these graded beds that represent the ejecta from the impact, as well as the sediment produced by the tsunami. At this newly discovered Tana site, what's interesting is these fossilized sturgeons that were killed on the day of the impact, as well as ammonites. The ammonites are a squid in a shell. They lived in the ocean thousands of kilometers to the south and were washed up into the river by the tsunami. In the gills of the sturgeon, they're filled with these glass beads that would have killed them immediately. So we have an actual fossil record of the day of the impact and the tsunami that was generated. Absolutely fantastic. The acidification would have caused a loss of sunlight that shows down photosynthesis, including the photosynthetic algae and plankton at the base of the food chain. And of course, that killed many of the shallow water fauna. Some of the octopuses and squids and Shellynotus that lives in deeper water and may have been scavengers were able to make it through. Dinosaurs, of course, were large. Their metabolic requirements were huge. They were probably warm-blooded. And they simply, once photosynthesis shut down, the herbivores starved to death. And of course, the pteropods had nothing to eat. And so the things that survived were scavengers. And it's not clear that there were many dinosaurian scavengers. And dinosaurs are too big to hide in a hole or hide under a tree. So they ended. Okay? In contrast, the Cretaceous mammals that lived in the nooks and crannies of a world dominated by dinosaurian giants managed to survive. Interestingly, purely carnivorous or herbivorous mammals did not survive. It was really the omnivores and the scavengers. And obviously, they emerged in a world rid of dinosaurs and within a few 100,000 years began to diversify. But worse things have happened in the past. So the greatest extinction of all time is the Permian extinction. 95% of all species went extinct, and it ended the Paleozoic era. Paleozoic means old life. Mesozoic means middle life. So the very words that we use to describe the periods of geological time are marked by these mass extinction events. Okay. So here's what the world looked like 255 million years ago. There was this Tethyan Ocean that was enclosed by continents, and all the continents were united together in this grand supercontinent called Pangaea. There was worldwide deserts, and there was a super greenhouse going on. The likeliest suspect for the Permian extinction is a supervolcano, another hotspot produced by mantle plume. That deposit is found in Siberia. It may have been up to 5 million square kilometers in area. It's about a kilometer in thickness, so about 5 million cubic kilometers of lava that just covered a vast landmass. What's interesting, about 2/3 of the lava volume were released right around 252 million years ago. And you can see all sorts of crazy things happen geochemically to the Earth. There was kind of a period of intrusion versus extrusion, and there was another big phase of volcanism in the Triassic that also caused serious effects to life on Earth. This lava volume was extruded in a period of about 30,000 years. Here's sort of a little block diagram that shows the intrusion. What's interesting is it intruded a sedimentary basin in Siberia. And that sedimentary basin contained the deposits of coal from the previous Carboniferous period. You remember the coals stored carbon and threw the Earth into an ice house. All of a sudden, the super plume releases that carbon and throws the world into a super greenhouse. So we see that these volcanoes are actually driving the CO2 cycles and releasing something on the order of 8 gigatons per year over a period of about 30,000 years, for a total of 85,000 gigatons of CO2. Now, I'll come back to this at the end of the talk, which we're actually getting fairly close to. The current release of anthropogenic CO2 is about 3 gigatons a year. And these numbers are not that far apart, okay? We've been doing it for 100 years. The Siberian traps did it for 30,000 years and released an order of magnitude more carbon dioxide than we'll ever get to, probably. And the results were pretty catastrophic, okay? In addition to the CO2, there was dust, ash, probably hydrogen sulfide, sulfur dioxide aerosols, and carbon monoxide, as well as halogens that can destroy the ozone. Okay, the effects of the eruptions were widespread. I already sort of very quickly went through some of the major consequences of volcanism, such as sulfates, halogens, carbon dioxide, and without going through all the details, the short story is they create mass havoc and mass extinctions. Okay. And of course, it's worth realizing that some of these things like carbon dioxide take hundreds of years to dissipate in the atmosphere and may stay in the oceans for longer. So the havoc on the oceans was extreme, okay? Whereas the hazards to terrestrial life through aerosols is a little bit less. So terrestrial life rebounded a little bit more quick than marine life. Okay. The kill mechanisms were selective. Animals with low metabolisms, like filter-feeding brachiopods, and these stalked crinoids that are related to modern sea urchins and sea stars, they have slow metabolisms and they went extinct. They're also calcifiers. They make their skeletons with calcium carbonates. If the ocean gets too acidic, it's hard to retain your skeleton. The more mobile animals with higher metabolic rates, like bivalves, mollusks, sea urchins, and gastropods or snails, survived the extinction. Many of the corals went extinct. The non-shell sea anemones survived, and they re-evolved skeleton-making ability to evolve into the modern scleractinian corals that make modern coral reefs. So in the talk abstract, I did promise I would talk about every mass extinction. We haven't got time for that, and I see I'm getting close to time, but I've got just a few slides left. So here are the 5 major extinctions, and it looks like large igneous provinces are either speculated or known to correlate with all of them. So it certainly looks like these massive mantle plume events are really dangerous. For a while there was excitement that maybe there were periodic asteroids or meteors that hit the Earth every 26 million years. That hypothesis hasn't really borne fruit, but it's certainly clear that Chicxulub played a big role in the Cretaceous extinction and may have played a role in some of the other ones. All right, so we're going to go back to the final few slides here, and then we'll have question period. So I'm looking at the ranking of the results. Interestingly, 41% of you suggested that anthropogenic warming will cause significant stress on many populations. And that's probably, you know, my guess is we're probably more in here. 5% of you suggested that anthropogenic global will literally destroy our planet. The IPCC report suggests that there's no possibility of that happening, but they say there is a 5% chance of 5-degree warming that would certainly cause extinctions of some species. So global warming will cause effects, and they could be modest to pretty severe. Okay. So just some final thoughts before we go to questions. So one of the points I want to make, you know, in the 30 or a few minutes we have is Earth is undergoing constant change. Plates are moving, continents are shifting, the climate's changing, and those changes occur over time scales as slow as hundreds of millions of years to tens of thousands of years. Okay, we can't stop Milankovitch ice ages. We can't stop plate tectonics. We can't prevent mantle plumes. And by and large, over history, with the exception of these catastrophic mantle plumes, life is usually able to adapt to those changes. Okay. However, given 4.5 billion years of Earth history, rarely Earth has a no good, very bad, rotten day. Okay. And those cause mass die-offs. Life has never gone extinct completely. There are always some organisms that seek refugia, whether it's in very deep water, whether it's burrowing in a hole while things are going crazy. And those Lazarus attacks that emerge in an empty world, and in general, they're able to take over. I would not be talking to you if the dinosaurs were still around. So we could argue that mass extinctions have benefit for the succeeding organisms that take over, but it's not good for the folks that go extinct. And generally, generalists versus apex specialists. So the more specialized your behavior, your feeding strategy, the worse off you are. You know, it's better to be a cockroach than a panda if you want to survive a mass extinction. Okay. I would say that, you know, anthropogenic CO2 emission levels are at a similar rate to the hypothesized levels that triggered the Permian extinction. Okay. Having said that, the absolute levels are still much lower. You know, there was 30,000 years of emissions that got the Permian world up to probably 2,000 parts per million atmospheric CO2. Right now we're at 400. During the Cretaceous period, it was about 1,000 parts per million in the Cretaceous super greenhouse, but for whatever reasons, that didn't cause a mass extinction. So the Earth can tolerate doubling of the CO2. It has done so in Earth history without major catastrophe. It's not so much the amount of CO2, it's the rate at which the change occurs and whether or not life can adapt. So clearly changing the rate of deliverability, the availability of carbon dioxide scrubbers, such as weathering, photosynthesis, calcifying organisms, and burial of organic matter as coal, all of those contribute to mitigating CO2. These mechanisms largely shut down at the end of the Permian, and drove the world into a very catastrophic state where life almost went extinct. Now, there is some good news. When I was a graduate student at McMaster in the 80s, Rush were talking about acid rain. And my favorite band, Yes, was talking about Don't Kill the Whale. And we were concerned about CFCs and the ozone layer. We managed to solve those problems with good policy and hard-run activism. The conservation movement is not going away. Every week in the spec, someone's talking about global warming, and every government and people on Earth are talking about it. Yes, there are climate deniers, but the fact that we're all talking about it means that we're concerned about it. The US spends more money on climate change than almost any other country, and you might not realize it because of all the climate deniers there, but there's plenty of folks in the US that really want to get on it, and entire states like California will ban the sale of gas-powered cars in 2035. Back in January, I was in India, and they are choking to death. The air is so bad. China's not much better. And China in particular is working hard to try to solve its pollution problem. Humans can't tolerate poisoning themselves to death. I remember being in Newfoundland in the 70s and coming to Toronto in the 70s and so excited to be in Toronto and shocked by the horrific pollution in Toronto compared to what we had in St. John's. So, Toronto now has air that's almost as clean as we enjoyed on the East Coast. So I'd say the trends suggest that we will pick away at the climate problem with science, technology, and technology may come to the rescue as it has done in the past. The big question, of course, is will it be too late? How much damage is already done? We know that we're already into about a degree of warming. And I would say that it's critical to investigate the deep time past to give us the idea of what's happened and how critical and how horrific things could really be. And I would argue that in many of my conversations with folks about global issues, the deep time perspective is commonly either not known or completely ignored. And I find that looking at the deep time record certainly has provided me a lot of perspective on global change. So I'll end there. Sorry for going a little bit over, but I think we still have probably 15 minutes or 20 minutes for questions. So I'll stop there and invite questions for anybody.
Hi there. Thank you so much, Janok. Okay, I'm just going to jump right in and take advantage of the time that we have left. I have a question here from Elaine, and excuse me, I'm just reading another screen. She asks, because these periods are cyclical, would we eventually be heading into a mass extinction without such extreme human influence?
So there's a lot of debate as to how cyclic these processes are. Mantle plumes cycle on scales of 50 to 100, a couple hundred million years. And it's not at all clear that every mantle plume has a flare up. So there is sort of a random element in it. So within 100 to 200 million years, we will probably experience another mass extinction. But when that's going to occur is anybody's guess. And yes, absolutely those things will occur. If there were no humans on the planet, we will absolutely, with no question at all, go into another ice age. The only thing that would prevent that is if some mantle plume managed to mitigate that with too much CO2. I guarantee you that there will be major earthquakes in California. And I guarantee you it will be cold this winter. But I can't tell you if we're going to have snow on Christmas Day or January the 5th, any more than I can tell you whether there's going to be an earthquake in California tomorrow or in the next year or two. But there will be one serious one in the next 1,000 years. And it's the problem with geology. We're good at saying that bad things can happen over long periods of time. It's much more difficult to predict on human time scales when these kind of catastrophes can occur. But things like mantle plumes, almost certainly we will be able to detect the effects of them long before they got truly serious.
Okay. I have a question from Ahmed here who asks, since historic CO2 release is not caused by fossil fuel consumption, why are we worrying about CO2 release due to human activity?
So the release of CO2 that caused the Permian extinction was absolutely caused by fossil fuels, right? Those fossil fuels were coal. The organic sequestration of CO2 through coal and peat was stuck in that sedimentary basin in Siberia, and it was vaporized by mantle plume. So it was a natural release of fossil fuels. Obviously, no one used coal for fuel at the end of the Permian, but we are burning coal today very quickly, and coal was burning at the end of the Permian because lava was igniting it. So indeed, the release of carbon stored in coal, oil, and gas is indeed a cause of global warming, and was the reason for the Permian extinction. So I would argue that what we're doing as humans is exactly what the mantle plume did in the Permian, and we're doing it at a similar rate. If we do it for 30,000 years, we will cause a mass extinction. Whether or not humans will be doing that for 30,000 years is very doubtful. It's almost certain that within 100 years or so, we'll have replaced coal with better technology. So I'm sure that we're not going to trigger a mass extinction, but we certainly will cause significant stress on many populations, and already are doing so through the anthropogenic emission of CO2.
Mm-hmm. Mm-hmm. So what will happen to us if the sixth extinction does happen? What will happen to humans?
Well, at some point you get into science fiction. As fast as extinctions are, with the exception of the KPG extinction, if an asteroid hit, you've all seen the movie, maybe you've seen the movie Deep Impact, that movie wasn't far from the truth. If an asteroid hit or meteor, it would be really serious. And if photosynthesis shut off, we may have the advantage of electricity in greenhouses to get us through. We may be able to, we would see an asteroid coming from a long way. The short answer is, if it's far enough away, we could probably send a nuclear device, and the smallest change in angular momentum of a bolide hurtling towards Earth would cause it to miss by a wide margin. So we could probably prevent an asteroid. A mantle plume we probably couldn't, but it would occur slow enough we could probably build technologies to survive the catastrophe. Whether or not we could build a sort of technological Noah's Ark to save the rest of life would be a big question. And of course, depending on how sci-fi fanatic you are, perhaps we could colonize another planet and get away that way. I don't know. But that gets us into the realm of science fiction versus science.
Yeah, I think I've seen that movie too. Okay, so we're going to change tack a little bit here. Devin asks, at what distance to Earth does an asteroid become too close to hit or enter gravitational pull? Mainly so on asteroid Apophis, and I hope I'm pronouncing that correctly.
Yeah, so I got that question earlier today, and I looked up Apophis. I think it's 380 meters in diameter, as opposed to 10 kilometers or 10,000 meters. So that asteroid would probably largely break up. Probably wouldn't have. I mean, it wouldn't be fun, but there's things like the Tunguska meteorite that hits Siberia back, I think, in the 1700s, or the Barringer crater, that's Meteor Crater in Arizona. So something that size could cause some local damage, certainly wouldn't cause a mass extinction. I'm not an astrophysicist or an astronomer, but just simple, plain old Newtonian physics and good rocket science. What you would do, you would look at the speed of the asteroid, its size. You can calculate its momentum. You could determine what force applied at what angle would knock its trajectory off. By just the further it is away, a tiny change in its trajectory will cause it to miss Earth by a wide margin. So, a reasonable force applied to an object very, very far away is enough to get it to move. Once it gets too close, you're out of luck, right? Then you're into deep impact, where you've got to maybe blow it apart and split it in two. The short answer is I can't answer that question, but anybody with a rocket science or engineering degree would be able to do those calculations pretty well. And if NASA saw something hurtling to the Earth, they would do those calculations, and they would probably, the world would get together and develop the technology to prevent that catastrophe from happening.
Okay, here's a totally different one. Do you believe that doom and gloom theories are appropriate during this pandemic? And I have to say, I got a couple of emails saying, why are you talking about this right now? It's so, depressing. So I don't agree, but anyway, what's your take on that?
Well, I would say that, the study of the history of our planet is fascinating. And, I mean, I'm quite happy to, my brother and I like World War II movies, so I mean, I've watched Save It Private Ryan in the pandemic, and it's an uplifting story about a dreadful time. We cannot ignore the changes that are happening in our planet today. Examination of Earth history gives us the knowledge to say, how did the world cope with these catastrophes? If we don't know how the world coped with catastrophes, how can we ever manage them ourselves? So I would argue that being in a pandemic puts the mind very solidly on the reality of catastrophes and forces us to think hard about how we're managing this one and how would we do a better job in the future. So I think I'm not saying we should revel in catastrophe, but the more work we do on understanding them and really understanding the physical interactions of process and consequences allows us to ask questions like, what would we do if that Apophis asteroid was a bit closer than we would like? Do we have the technology to get out of the way? As opposed to saying, oh, we should just all watch Jerry Lewis, for example, or Seinfeld, which I'm also doing. I missed all the Seinfeld episodes, and I'm laughing my guts out watching reruns of those during the pandemic as well.
I'd also recommend Schitt's Creek for all the Mac grads out there. So
if
you haven't seen it, yeah. Nothing to do with geology, but a great little Mac connect there. Okay, Peter asks, how does this carbon dioxide emitted from brush and forest fires this past year compare with that arising from human activity? I think we all worry about that kind of
so
catastrophe.
Forest fires are the same as so forest fires, essentially it's burning fossil fuels, right? Wood is a fuel, and forest fires emit more CO2 in the region than traditional fossil fuels like coal and gas. The difference is, when you go to places like India and China, North America, Europe, you realize everybody's driving cars. And everyone's using fossil fuels everywhere all the time, 24/7, right? Forest fires are local, they're periodic, and they're area restricted. So the overall budget of fires is low globally. They do produce a lot of CO2 locally over short periods of time, but the global budget is pretty low compared to oil and gas and coal. So they're not significant in terms of the global CO2 budget, but they are concerns locally. And obviously, if you have worldwide fires, such as you had in the Cretaceous, or in Siberia, the other thing I didn't mention is when the Deccan traps covered India and the Siberian traps covered Siberia, they burned all the forests. I remember flying in a helicopter over Hawaii, seeing trees being burnt by the lava as it flowed over the trees. So you can have massive deforestation by these large igneous provinces. And again, those will contribute to the massive amounts of CO2 in addition to the coal that's already been buried. So the burning of buried fossil fuels and forests are certainly significant. But the modern day burning of forest fires is troubling, but the overall budget to CO2, I don't think is as high as the regular burning of fossil fuels for transportation and manufacturing.
So different reason to be concerned, but not the CO2. So if you could sum up, what are the key pieces of evidence repeated in the past that we should consider for the future? And I guess that would be referring to human, like our human impact on the climate. And
so I think, if you think about the theme of this talk, what deep time scientists want to do is you want to get at rates and amounts and causes and consequences. So we're now at a threshold in our science where the ability to date rocks is getting better and better and better, more precise. So you can now date a 100 million year old rock to a precision of 0.02%. That's plus or minus 20,000 years. That's the range of the so-called Milankovitch climate cycles. So that means we can now understand the details of a specific climate cycle and when they occurred and what they caused, down to timescales of tens of thousands of years. Humans live at timescales of 100 years. Civilizations last about 1,000 years. So there is this gap between what what geologists can figure out at scales of 10,000 years and what are relevant to human and civilization scales. For that record, we need to look at the younger record, which we call the Pleistocene, where carbon dating can date things down to scales of hundreds to a few thousand years. And of course, there's many, many folks looking at global change from the perspectives of things that have happened over the past few 100,000 years to a few million years, and of course, deep time. The larger the window that you look at, the greater likelihood that you'll find those really big catastrophic events. And I would argue that by understanding the causes of those events, whether it's asteroids, super plumes, climate change, allows us to look at ourselves and the effects of our own effects on planet Earth with some sobriety and some perspective. And the other thing I'll say is, again, another hopeful thing, back in the 70s, there was a book called The Population Bomb, The Limits to Growth, and they predicted that we were going to run out of food, that we were going to run out of resources. In response to that, a country called China instituted their one-child policy because they felt that they were going to starve to death. Well, in the end, we became self-sufficient in food. The crisis never happened, and China's now realized, oh, okay, we didn't need to do that. And now they're paying people to have more than one child. Rich countries like Japan, Eastern Europe, they're having negative population growth because guess what? People with wealth and education don't want to have as many kids. They're expensive. So now the concern in many Western countries is how to keep the population at a level. The way that we do this in our great country is through immigration, right? We basically invite the populations from countries that have too many people, say, well, come to Canada. We still don't have enough people here. But of course, we're still self-sufficient in agriculture. There's no indication that's going to go away. And as I said, we can anticipate concerns. We can stop CFCs. We've stopped SO2. The humpback whales are back. We've managed to conserve those. So if you fly over Hawaii, you'll see them bathing in the waters. And I remember when, one of my favorite bands, Yes, was writing about the death of the whale, and there were Star Trek movies about humpback whales. So, a lot of these predictions from pop stars and Star Trek movies turned out not to be true. We've accomplished a lot. So that's where the hope is. The requirement is that we have to work together globally. And to a degree, you have to trust the science. We have to recognize that science pushes our knowledge, pushes our uncertainties. And some science, like the population bomb and the limits to growth, turn out to be predictions that weren't that great. So anytime we try to make predictions, they're guaranteed not to be great. However, they do allow you to at least start to thinking about the risk of things that can happen in the future. And that's kind of what really what the idea I want to leave you with is we're the only species we know of that's able to make predictions about the future and do something about it. Cockroaches can't make predictions about the future, but because they're generalists, they manage to get through everything.
Well, I think that's a good note to leave it on, a hopeful note and a trust in science note. I like it. So thank you very much for your time tonight, Janok. We really appreciate you putting this together for us. It was extremely informative and just packed full of information. So thank you very, very much. And thank you to our audience for joining us. We're really grateful that you're interested in hearing from our wonderful alumni and faculty. And thanks for tuning in. I'll just say that you'll be getting a survey to your email inbox soon. And we really appreciate your feedback. And when you respond, we look at it all. So please do answer it and give us your feedback. Thanks so much. Have a wonderful evening. And thanks again.